Hi, so today we're going to be looking at another problem on quantum mechanics. And well, in this case, we have a system represented by this Hamiltonian given in matrix form, and we have two observables, A and B. And well, just omega, lambda, and mu are all positive real numbers. And just really quick, an observable in quantum mechanics is some physical quantity that can be measured. In this case, H tells us the probability of measuring some energy states, which as we know are quantized, that is, they are discrete. We have E1, E2, and so on. A and B are some other two observables, which also give us some probabilities and expectation values of some physical quantity, which we call A and B. And well, we are asked to calculate the eigenvalues and eigenvectors of H, A, and B. So let's just do this real quick. So let's start by H. I want you to notice that H is already diagonalized, so our eigenvalues are going to be H omega, 2H omega, and 2H omega. But if you don't trust me, we can do this really quick and just write H omega 0, 0, 0, let me just write H omega minus E 0, 0, 2 H omega minus E 0, 0, 0, and 2 H omega minus E. This determinant is nothing but H omega minus E 2H omega minus E and 2H omega minus E. And we are imposing that this is 0. As we can see, we already have that the eigenvalues of H are, let me just write this here. Okay, so for H, we have that E1 is equal to H omega, because in that case this will hold. So we have H omega, and E2 is equal to E3, which is 2H omega. Because in this case we have 2H omega, we have that this is 0. So now all we have to do is to find the eigenvectors. First of all, let's start with the eigenvectors associated with E1 equals H omega. So we can just write this in the system of equation form, and we have that H omega minus E1 alpha plus 0 beta plus 0 gamma plus 0, that 0, what is this, 2H omega minus E1 beta plus 0 gamma equals to 0, and 0 alpha plus 0 beta plus 2H omega minus E1 equals to 0. So in this case, E1 is H omega, so this really is just 0, and this just gives us 0 equals to 0. In this case, well, we have 2H omega minus H omega is just H omega beta equals to 0, and in this case, H omega gamma equals to 0. So, for these two equations to hold, beta and gamma must necessarily be 0. But notice that alpha can be any value that we want, because it will not affect our system of equations. So if you don't know where the system of equations comes from, it's just the standard eigenvalue problem in which we have a matrix H minus E times identity times some vector, which we have assumed has components alpha, beta, and gamma, and we just multiply it to get a system of equations. But well, yes, alpha can be a real number. So all the eigenvalues associated with E1 are represented by our alpha times, well, not really, just our alpha 0 and 0. And we can express this as alpha times 1, 0, 0, and we choose the eigenvector for which it has norm 1. So in this case, we will choose that alpha is 1 and get 1, 0, 0. So our first eigenvector is 1, 0, and 0 for H. And for E2, let me just erase this a bit better. So we have our first eigenvector, phi 1. The next one, well, it will be E2 equals to E3 equals to 2H omega. And to find it, well, again, we have some alpha, some beta, some gamma equals to 0. Let me just write it like this first, because we're going to be using it for the other two. So we have to subtract E2 from A1. So here we will have H omega minus 2H omega, and here we'll have 0, 0, 0, 2H omega minus 2H omega, 0, 0, 0, and 2H omega minus 2H omega. Notice that this is 0, and this is just minus H omega alpha equals to 0. For this to hold, we necessarily need that alpha is 0, because in general H omega is not 0, because omega is just a positive number, it's not 0. So what we have is that in general our eigenvector in this case, let me just call it phi, is just, well, alpha is 0, beta can be any value that we want, and gamma can be any value that we want, so we can just write beta and gamma. And we can actually just represent this as, well, beta 0, 1, 0 plus gamma 0, 0, and 1. This means that we have two eigenvectors. One of them, which we will call 2, is just 0, 1, and 0, because we are choosing beta equals 0 and gamma equals 0. So beta equals 1 and gamma equals 0. And we can also choose 0, 0, and 1. In this case, beta equals 0 and gamma equals 1. So these two linearly independent vectors constitute a basis of the kernel of E2, E3 equals 2H omega. That is, well, they are a linear combination of them, which is this one, can give us any eigenvector with eigenvalue E2 and E3. So we have that the two eigenvectors are 0, 1, 0 and 0, 0, 1. We can erase all of this and get on with our next observable. So as you see, it's actually just a really easy problem. We find the eigenvalues and then the eigenvectors. And I hope that you can see this well. Let me just try to put it a bit clean. For A, well, in A in this case it is not diagonalized, so it might be a bit harder, but not too much. So we have 0, lambda, just write like this, lambda, 0, 1, 0, 0, 0, 0, and 2. Minus lambda, and minus lambda. This is just, sorry, a 1. No, sorry. We have the following. We need the determinant of A minus, let me just call this A times the identity and goes to 0. So here we subtract an A, we subtract an A, and we subtract an A. And we'll multiply by lambda because we have a lambda there. So lambda, and 2 lambda. So let's just write the determinant of this matrix, this notation. We just have minus A times this is just A squared times 2 lambda minus A this will be 0, this will be 0, minus 0, this, and 0. So this will be lambda squared times 2 lambda minus a. And we are imposing that this is 0. So one possible eigenvalue is a equals to 2 lambda. If a equals to 2 lambda, this is 0 and this is 0. But if a is not 2 lambda, we can divide by this term and this term because it is not 0, and we get that a squared equals to lambda squared, from which a2 equals to plus lambda and a3 equals to minus lambda. I have the 3 eigenvalues. So let me just write it here, maybe. A1 equals to 2 lambda, a2 equals to minus lambda, or plus lambda, and a3 equals to minus lambda. And this is for the observable A. Now all we have to do is to solve our system of equations to find the eigenvectors. So to find the eigenvectors, we will start with A1 equals to 2 lambda. And our system of equations is just as before. We are going to write it like this. So let me just write it really quick. If you need anything to understand what eigenvalue problems and all of these things are, and you're not used to it, you can check out my channel. I will have some videos explaining what the eigenvalue problem is and how to find the eigenvectors and eigenvalues. So well, in this case, we just have to write our A matrix, which is just 0, lambda, lambda, 0, 0, 0, 0, 0, 2 lambda, and we have to subtract on the diagonals to A1. So this will be A1, A1, and A1. Notice, A1 is 2 lambda, so in this case, this equation just gives us 0 equals to 0. In this one we have minus 2 lambda, alpha, plus lambda, beta, and this is 0. On the second equation we have lambda, alpha, minus A1, sorry, minus 2 lambda, beta. And this is what we have, and yes. So, for this to hold, we have that alpha must be equal to beta over 2. Right? Right, from this one we get alpha is beta over 2. And if we substitute on the other one, we get that lambda times alpha, which is just beta over 2 minus 2 lambda. Beta has got to be 0, but this is that lambda halves minus 2 lambda, beta is equal to 0. This can only hold really if beta is 0. So this is what we will get, that beta is 0, and this implies that alpha is in turn 0. What about gamma? Well, gamma doesn't appear in our system of equations, so gamma can take any value that we want. In that case, we have that the eigenvalues of A, let's just call them psi, like this, are given by gamma 0, 0, and 1. So our first eigenvector is 0, 0, and 1. So let's just write this. So our first eigenvector, psi 1, is 0, 0, and 1. Notice that it coincides with phi 3, but there's actually no problem. Now, if instead of A1, we wrote A2, which is just plus lambda, we will have here some lambda, and some lambda. In this case, we get minus lambda alpha plus lambda beta equals to 0, lambda alpha minus lambda beta equals to 0, and lambda gamma equals to 0. So gamma has to be 0 because lambda is not 0, so gamma is 0, and alpha has got to be equal to beta for this to hold, so alpha equals to beta. So our second eigenvector is just, well, alpha, beta, and 0, but beta is equal to alpha, so we choose this. Sorry, what we choose is that alpha has got to be 1 over the square root of 2, so we can have a normalized eigenvector. 1, 1, and 0, okay? So this is our second eigenvector for A. 1 over the square root of 2 of 1, 1, and 0. Lastly, we have to calculate the eigenvector corresponding to minus lambda. So let me just do this real quick. In this case, we get this, and this. So we have lambda alpha plus lambda beta equals to 0. This one is just lambda alpha plus lambda beta equals to 0. You see it's the same equation really. And 3 lambda gamma equals to 0. Again, gamma has got to be 0. And what about alpha and beta? In this case, they are related by alpha equals to minus beta. So our third eigenvector is 1 over the square root of 2 of 1 minus 1 and 0. I'm going to go a bit faster now because we have to do another observable. So I tried to do all the steps beforehand in these two eigenvalue problems, but from now on I'm going to go a bit faster. So if you have any doubts, just watch the other ones closely and try them yourself. So we already have solved the eigenvalue problem for A, and I'm going to write B right here. Okay, so I decided to organize it like this so we have more space, and well, I also re-rolled everything so you can see it a little bit better. So we were dealing with the B operator, and we are to find the eigenvalues and eigenvectors. So just really quickly, we have 2 mu 0, 0, 0, 0, 1, 0, 1, 0, and we have to subtract some b here and here, and this determinant is just, well, 2 mu minus b times b squared minus, well, this is, sorry, let me put this here. Oh, I made a mistake here. This is not a 1, but rather a mu, and this is another mu. Okay, so 0, 0, this one is 0, 0, and we just have 2 mu minus b mu squared, and we are imposing that this is 0. So one solution would be that b is 2 mu. In this case, we get that this is 0, this is 0, and the equation holds. If b is not 2 mu, then we can divide by this, and this will cancel out, and we have that b squared minus mu squared equals to 0, but this just means that b2, well, that b is plus or minus mu, and so b2 is mu and b1 is minus mu. So let's just write these eigenvalues here, 2 mu, mu, and negative mu. Now, what's next? We have to find the eigenvectors. So the first eigenvector is the eigenvector associated with b1 equals to mu. So if we consider b1 equals to mu, then we have that our system of equations, as always, is just alpha plus beta plus gamma this is 0, and alpha plus beta plus gamma. And as we see, here we just have to write, in this case, b minus the eigenvalue, b1 in this case, times the identity matrix. So in our case, we will have 2 mu minus b1, here just 0, 0, 0, 0 minus b1, 1, sorry, not 1 but mu, I always get mixed up with that, sorry, mu, because we have to multiply mu times all elements in our matrix. And lastly, 0 minus b1. Now, b1 is 2 mu, so this is 0, this one just gives us 0 equals to 0, minus 2 mu times beta plus mu gamma just gives us 0, and this one is mu beta minus 2 mu gamma equals 0. I'm sorry about that, this is my computer. And from this, we get that gamma is just 2 beta. Substituting on, right, from this one you get that gamma is 2 beta, assuming that, well, mu is not 0 because, well, we said before that mu was greater than 0, it was a positive real number. And what else? Well, if we substitute here, we get that mu b minus 2 mu gamma, which is just 2b, is equal to 0, and this just means that beta times this one, let me just check, 2 beta for minus 3 mu is equal to 0. So this will only hold if beta is 0, so this implies that beta is 0, and this in turn implies that gamma is also 0. But what about alpha? As we said, alpha is not contributing anything to any of the equations, so it can be actually any value. So our first eigenvector has the general form 1, 0, 0. But we want it to be normalized, so we will choose that alpha is just 1. So we get that this is our first eigenvector. Sorry. 1, 0, and 0. And let me just write the following ones. Okay. What's the next step? Well, to find the eigenvector corresponding to b2, which is just mu. In this case, we just have b2, b2, and b2. So 2 mu minus b2. Well, mu minus 2 mu minus mu is just mu alpha plus 0 equals 0. Minus mu, sorry, 0 minus mu beta plus mu gamma is just 0, and 0 mu beta minus mu gamma equals to 0. So alpha is 0 and beta equals to gamma. So our eigenvector is just beta 0, 1, and 1. Let me just write it here. Well, of course, to normalize it, we have to divide by square root of 2. So we have 0, 1, 1, and 1 over the square root of 2. And lastly, we just have to put a minus sign here to get b3. In this case, get b3, b3, and b3. What do we get here? Well, this is 3 mu in our case, right? 2 mu minus mu is just 3 mu. In this one we get a plus. This one remains with a plus. Here we get a minus, and this remains with minus. So in this case, we have that A is 0 again, but beta equals to minus gamma. So our third eigenvector is just this one. Or you could also choose this one by choosing another beta, but in our case we will just choose this one. And the reason that we can choose either this one or this one is because we have any constant here that we want. So if we choose, for example, -1, this will change, but it doesn't really matter for our purposes. We're just going to choose this eigenvector and divide by its norm. 0, 1, and -1. So this is the first step, the first part of our problem. We want to find the expectation values of H, A, and B if we have a state which we will call S at time equals 0, which is given by C1, C2, and C3. Okay, this is C2, this is C3. And we have the condition that C1 squared plus C2 modulus squared plus C3 modulus squared equals to 1. The definition, the expectation value, is the sandwich operator between our state, psi, and our operator. This sandwich just means that we're taking the dot product between this term, this ket, this bra psi, and this term, which is just A applied to the ket psi. In our case, instead of psi, we got S0, so, for example, the expectation value of H when we are in the state S0 is the sandwich of S0, H, S0. So we know that S0, let me just write here, that S0 is just C1, C2, and C3. But what is this is the ket. What is the bra? Well, the bra is just a complex conjugate transposed. So the bra of this ket is, well, we're taking the transpose, right? We're writing a column vector as a row vector, and we are taking the conjugate of all of its elements. So this would be our bra, and well, we don't need really a 0, but actually H multiplied by H0 applied to it. So when we apply this operator H, Hamiltonian, to our state, what we get is that we only have to multiply this matrix by that. So we have H omega 1 0 0 0 2 0 0 0 2 times C1 C2 C3, and this is, well, H omega, and this will be as another column vector, and C1 2C2 and 2C3. So we have H omega, or ket, or bra, sorry, C1, C2, C3, and C1, C2, C3. This is complex conjugate, and that's actually everything we have here. This would be C1 conjugate, sorry, conjugate times C1 is just its modulus squared plus 2 C2 modulus squared plus 2 C3 its modulus squared. So let me just erase this. Well, let me just get this here. We'll need it afterwards. So notice that if we take one C2 out of here and one C3 out of here, we end up with H omega C2 squared plus C3 squared plus, let me just write it like this, C1 squared plus C2 squared plus C3 squared. And this is 1 because we have that condition, so we end up with C2 squared plus C3 squared plus 1. This is expectation value of the energy when we are in state S at time 0. So let's just write it here. The expectation value is just h omega 1 plus c2 plus c3 modulus squared. So let's just do the same for the A operator and okay, erase this again, and the B operator. So when we're dealing with the A operator, we have that this expectation value is at when we are in this state, right? This state right here is just, well, the sandwich between our state and our operator. In this case, we have the same as before, C2, C3, but here we have to multiply A times, well, this will be A times S0. So we multiply by the matrix, and let me just put it like this. We have to do this multiplication, 0, 1, 0, 1, 0, 0, 0, 0, 2 times C1, C2, C3. This will give us, well, lambda can just come out of here. We get this times an calling vector, which in this case is just C2, C1, and 2, C3. And this is just lambda times C1, C2, so complex conjugate, C2 plus C2 complex conjugate, C1 plus 2, C3 squared. This would be expectation value of A. And where do I write it? Let me just put it here if it's not. Yeah. Okay. Yeah, that will be it. Now we have to do the same for B, and to save some time, we just write B, and instead of this matrix, we will need the B matrix, which is this one. So mu 2, 0, 0, 0, 0, 1, 0, 1, 0. What this would give us? This would give us 2C1, C3, and C2. In this case, we will get 2C. Let me just do this. We'll get 2C1 squared plus C2, C3 plus C3, C2. That will be our expectation value. Yeah, that will be it. So this is the second part of our exercise. And well, the last part of our exercise is to find the time evolution of our initial state. So we want to find the time evolution when our initial state was what was it? It was just C1, C2, and C3, and we had that C1 plus C2 plus C3 equals to 1 when we have this squared. Okay? So how do we find this? Well, as we said, the time evolution has to satisfy the Schrödinger equation, and the most general solution to the Schrödinger equation, if we represent it with the eigenvectors of the Hamiltonian, is given by this expression. So, to find the time evolution, we said we have to use this equation, right? Which is just the solution to the Schrödinger equation. Notice that instead of C, I wrote D because we also have used the letter C for these components, and well, we might get mixed up. So, what is D1? Well, D1 is just the first eigenvector doing the inner product with our initial state, and this is just 1, 0, 0, C1, C2, C3, and this gives us C1. For D2, doing the exact same procedure, we get that this is C2, and for D3 we get C3. Just check it yourself, but this is what you get. So we can just expand this sum as D1. Well, D1 is just C1, so e to the minus I E1t over h times phi 1. And notice that I have not written T0 because in our case T0 equals 0, right? We're at the initial time 0. Plus C2, right? Because D2 is C2 times e to the minus I E2t over h phi 2, and lastly C3 e to the minus I E3t over h phi 3. This will be the time evolution of our system. And well, we can actually just replace the E1, E2, and E3 by the corresponding value. So E1 will be h omega, h with h cancels out, so we get omega t. E2 is just 2h omega, so it cancels out, and we get 2 omega t. And C3, well, E3 is just the same as E1, so we get 2 omega t. Yeah, and this would be the time evolution of our system. So let me just here, because we are going to need it now. The next thing that we're asked, and this is the last thing, is to calculate the probabilities of obtaining each eigenvalue. That is, if we measure h on this state, we can either get E1, E2, or E3. There are no other possible values of energy that we can get. So what is the probability of obtaining E1? Well, it is given by the third postulate of quantum mechanics, and it is just the sum over I of alpha and I st squared. What is alpha and I? Well, alpha and I are just the eigenvectors of the Hamiltonian. And so, for example, in our case, E1 has a corresponding eigenvector phi 1. And there's only one of them. So I sums over all the eigenvectors corresponding to the same eigenvalue. In our case, we only have one, so we get that we only have to write phi 1, phi 1, st, and this squared. How do we do this? Well, we have to do the product between phi 1 and st, and notice that st, well, we can write it as follows. At c1 e to the minus I omega t phi 1 plus c2 e to the minus I 2 omega t phi 2 plus c3 e to the minus I 2 omega t phi 3. What is this inner product? Well, we know that phi 1 and phi 1 are the same vectors, so we would get c1 e to the minus I omega t. Phi 1 and phi 2 are orthogonal, perpendicular. You can do the dot product if you want to check. So this will be 0, and the same happens for phi 3. So this is what we get. So the probability is c1 e to the minus I omega t modulus squared. The modulus of any complex exponential is just 1, so we get this. Likewise, what is the probability of obtaining E2 or E3, which are just the same values? Well, we have to sum over I all the eigenvectors. Let me just write this. Let me just write this like this. And I st. So, what are all the eigenvectors corresponding to this eigenvalue? Well, in this case, we have two. we have that corresponding to this eigenvalue, we had phi 2 and phi 3. So if we expand this, we will get that this is phi 2 st squared plus phi 3 st squared. And how do we do this? Do we do this? Well, just the same as before. We put phi 2 here, and phi 2 and phi 1 are orthogonal. These ones are the same, and this is orthogonal, so we get c2 e to the minus I 2 omega t. Taking the modulus squared, we get that this is just c2 squared. Plus, all doing the same for phi 3, we get that it is orthogonal to this one and this one, but not to this one. So we get c3 e to the minus I 2 omega t. Taking the modulus squared, we just get c3 squared. So these are the probabilities corresponding to the Hamiltonian. Okay? And where do we write this? Well, let me just write square. And notice that if we add this probability and this probability, we get this plus this plus this, which is just 1. Meaning that all the possible energy values are either E1 or E2, which is equal to E3, 2h omega, 2h omega. Now, if we want to measure the probability of obtaining some value for A, well, we can start with the first eigenvalue, which are the only possibilities, right? When we have an operator, the only possible values that we can get when we measure it are its eigenvalues. So in this case, we have A1, we have this sum over all the eigenvectors, and what are the eigenvectors corresponding to E1, to A1? Well, in our case, we only have this one. So we have this times this squared. So let's just check this one again. In our case, phi 1 times st, well, phi 1 really is nothing but phi 3. So this would be the same as writing phi 3 st, and we know that this gave us c3 e to the minus 2 omega t. So this is just c3 squared. Oh, that was easy. The next one, the probability of measuring A2. Well, it's just the sum again. How many eigenvectors correspond to A2? Well, just one, phi 2. So we have phi 2, that product with s of t squared. So let's just do this product right here. We have this times partial evolution, which let's just write it like this. Plus c2 e to the minus I2 omega t phi 2 plus c3 e to the minus 2 omega t phi 3. So what we have to do is to multiply this one by each of them. So let's just do it here. So psi 2 times phi 1 is just 1 over square root of 2. 1, 1, 0. No. Yes, 1, 1, 0. 1, 0, 1. Well, this just gives us 1 over the square root of 2. If we do the same for phi 2, we get this times, so this would be a 0, right? Times 0, 1, 0. This just gives us this times this, 1 over the square root of 2. And psi 2 times phi 3. Again, 0, 0, 1. This times this is just 0. So this product gives us 1 over the square root of 2 times this, 1 over the square root times this. So this is 1 over the square root of 2 corresponding to this one times c1 e to the minus I omega t over the square root of 2 plus c2 e to the minus omega t over the square root of 2. And we can express this as, well, one half comes out of all of this. Well, let's just put it like this. Okay, so this would be our probability, and we can't really simplify it more, we could expand it, but, well, let's just keep it like this. c1 e to the minus I omega t plus c2 e to the minus I omega t, I2 omega t. And if we do the same for psi 3, we get, well, 1 over the square root of 2 with the exact same expression, but with a minus sign here. If you don't trust me, just check it yourself and you'll see that you get this. So the probability of A measuring A3 when we measure A is 1/2 c1 e to the minus I omega t minus I2 omega t squared. These are the two probabilities, and yeah, so the probability of A1 is this one, the probability of A2 is this one, and the probability of A3 is this one. Because I'm running out of space, I don't think I'm going to write this one up there. I'm just going to erase and do the last one for B. So really for B, we have to do just the exact same procedure. Probability of B being B1 is just, well, there's only just one eigenvalue, which is phi 1 times s of t squared, and phi 1 is just the same as the other phi 1, so we can do this really quick and just say this is what we get. If you want to do it more carefully and more slowly, you can do it yourself and check if you get the same answer. For B2, we get another eigenvector, phi 2, and well, let's just do the product between phi 2 and phi 1. Well, it's just 1 over the square root of 2 of 0, 1, 1 times 1, 0, 0, 0, 0, they're orthogonal. Phi 2 times phi 2 is just the same, changing 0, 1, 0, with 1 over the square root of 2. And for the last one, yeah, we get the same. So if we multiply phi 2 by that, it's orthogonal to phi 1, is 1 square of 2 times the terms from C2 and C3. So C2 e to the minus I2 omega t plus C3 e to the minus I omega t2 modulus squared. This will be just 1/2. We can actually take this out, and the modulus would be 1, so the modulus of C2 plus C3 squared. For B3, which is just the last thing we have to do, we get phi 3 st squared, and this is just, well, phi 3 times, let's just do it, phi 3 times phi 1, phi 3 times phi 2, and phi 3 times phi 1, phi 3 Well, this one just gives us 0. This one gives us 1 over the square root of 2. And this one gives us minus 1 over the square root of 2. Yes. So we get 1/2. Well, let's just say 1 over the square root of 2 times C2 minus C2 e to the minus I omega t minus C3 e to the minus I to omega t, and this is 1/2 C2 minus C3 squared. And this would be the last probabilities, and that will be everything for the exercise. As you see, it took a lot of time because we were actually asked to do a lot of things, but each and every part of the exercise was actually just really easy by themselves. So, well, I hope you enjoyed the video, and we will make more exercises on quantum mechanics. See you in the next video.